Tutors. Today I want to talk to you about a particular theory of what gases are and how they behave, called the kinetic-molecular theory of gases. Now this is particularly important historically because we didn't know what molecules were, we didn't know what atoms were, so we didn't have a way to connect the big picture, the macroscopic picture, such as the mass of a gas, the volume of a gas, to the microscopic picture, the number of particles, the way the particles collide, and how that informs what the temperature is, and many other microscopic properties of gases. So the kinetic molecular theory says that gases consist of very small particles known as molecules. That seems really surprising. We think everything's made out of molecules, everything's made out of atoms, but at the time, say 1738, when Bernoulli first introduced this idea of the kinetic molecular theory, this was not known. We didn't know the microscopic picture of what a gas was. We could measure its mass or its volume, sometimes we could see the color, but we didn't know what it was actually made of. The other key thing here is that the total volume of the individual gas molecules is basically zero compared to the volume of the gas as a whole. Now, you might ask then, how do you define the volume of a gas? A bunch of zeros added up is still zero. Well, you define it by the cloud that encompasses all of the gas molecules. So another way of stating this first principle is that the distances between molecules are astronomical compared to the size of the individual molecule. So say if you had one gas molecule in a room, you might, under kinetic molecular theory, say that there was maybe one or two other gas molecules in the entire room if you scaled up the comparison between one gas molecule and made the gas molecule visible. So there is an extremely large distance between gas molecules compared to the size of the gas molecules. Again, we want to think of compared to the size because there's not actually a large distance. We might have a volume of a liter in a mole of gas molecules, but we do want to keep in mind that molecules are very, very tiny things. Relatedly, so if the molecule is such a tiny thing, we say the number of molecules in a gas is so large that we can use statistical principles. We can't track the movement of every single molecule, that would be ridiculous and really impossible, but we can use statistical methods to link the microscopic and the macroscopic or everyday size picture. Another tenet says that the molecules are in constant, random, and fast motion. They never stop moving. They move very quickly, and the motion is random. The collisions are random. They're not at any fixed path. They're not at any fixed path towards each other in collisions. Nothing like that. In those collisions, which is the only time when, under this theory, the molecules actually interact, the collisions are elastic, meaning that no energy is lost. This is the same as saying that there are particles that are point masses, and they interact with each other in a way that doesn't lose energy. There's no squishing of the gas molecules because they're basically zero size. The last thing that the kinetic molecular theory says is that interactions among molecules are negligible. So this isn't true of real gases, so this really highlights that this is a model of gases and doesn't tell us everything about how gases behave. Interactions among molecules are negligible means when the molecules aren't colliding, there's no intermolecular forces between them. They're basically independent of each other, so that we can simplify the behavior of a gas a lot by assuming that, say, water vapor doesn't have hydrogen bonding in it, or a charged gas doesn't have polar interactions or dipole-dipole interactions. We really take a very simple model of gases. Now, part of the reason for this is that this is a model that comes about in the mid-18th century, the 1750s-ish. So we really didn't even know what a molecule was, so we really want to simplify our model of a gas. But another part of this is still relevant today. It's not just a historical artifact, it's also because this model fits even real gases very well. There are little tiny corrections because the volume of a molecule isn't actually zero. There are little tiny corrections for the intermolecular forces, and the corrections are of different sizes. In other words, the model fits more or less well depending on what gas it is, what intermolecular forces there are, if it's really high temperature or pressure, so that the molecules are really close together and the distances are actually smaller. But this is a really good model in general of a gas, and it led to things like the ideal gas law or the smaller laws that relate volume and temperature or volume and pressure. Those all came about as a result of applying physics, or really looking at graphs, saying, how can we explain this relationship between volume and temperature? Well, we can explain it in terms of the microscopic picture of molecules. So this is a model, which means that it's not exact like anything else in physics and chemistry, but it is a very useful model and useful for problem solving as well as understanding the properties of gases. The last thing I'll say is that this model basically means that oxygen gas and nitrogen gas and fluorine gas all behave the same way under this model. It doesn't matter actually what the mass of the elements that forms this gas, of the molecule that forms this gas is, because we're treating them as things with zero volume, they really behave the same way. There is a mass to the gas, and that is different between different chemicals, but that's the only thing that's different. And that's a really powerful way of thinking of things where we're not worrying about the identity of the chemical. That's it for now, and more next time.